So on look 2 and 1, there's a 0 here, so that's perfect. There's a 0. So I'm going to say R1 minus the same signs. I'm going to subtract 2R2, and I'm going to place that into R1. So 3, that's going to stay the same, and the last 2 rows stay the same. So 2 minus 2, 0 minus 0, 13 minus 2 times -1, that would be 15. So notice I only have 2 entries that are non-zero in the first row, and they're scalar multiples of 3. So I'm going to say 1/3 R1 goes in R1. So I can write my reduced matrix. And I don't know, I don't think he's mentioned this yet, but since there's a diagonal of 1s and the rest of the entries on this 3x3 are 0, this is called the identity matrix. So the identity matrix is augmented with our answer. So I can rewrite this as a matrix equation with my identity matrix being multiplied by my variables, and it's equal to my answer, 5, -1, 0. So the identity matrix is a fancy way of just saying 1 times, the variables is equal to the numbers. And so I can say x equals 5, y equals -1, and z equals 0. And that's what I was talking about, the z equals 0 from the first equation. How we have the same x entries, same y entries, different z entries, but they are supposed to equal the same number. So that tells me that it doesn't matter what z is. Well, it does matter. Z would have to be 0 because these numbers are the same and those numbers are the same. But I definitely needed that last equation to tell me the rest of the information. You need 3 equations if you have 3 unknowns to have a consistent and unique system, or a consistent system with a unique solution. Okay, so I'm going to do the same thing. I'm going to take all my coefficients and put them into a matrix. So 2, 6, -4, 8, 3, 10, -7, 12, -2, -6, 5, -3. So I just went ahead and augmented it. And then there's something special with the first row. The first row is a scalar multiple of 2. So my first row operation is going to say 1/2 R1 to R1. So 1, 3, -2, 4. And then the other 2 rows don't change. So my first 0 needs to be in the bottom left corner. So the easiest is to use the first row because there's a 1. So I'm going to say 2 R1 plus, since they're opposite in sign, R3, and I'm placing that in R3. So the first two rows aren't changing. So 2 minus 2 is 0. 6 minus 6 is 0. Negative 4 plus 5 is 1. And then 8 minus 3 is 5. And so right off, I got my first part of my answer, part of the solution set. I got that x3 is 5. And then next, I need to work on getting that 3 to be a 0. I can play off the first row again. So I'm going to say 3 R1 minus, since they're opposite in sign, R2, and that's going to be placed into R2. So 3 minus 3 is 0. 9 minus 10 is negative 1. Negative 6 minus negative 7 is positive 1. And then 12 minus 12 is 0. And then my last row, I don't even want to touch, since my last row is perfect. And then you notice the middle row, I have 2 non-zero entries. And so I want that first non-zero entry to be a positive 1. So I'm just going to scale the middle row by negative 1. So negative R2 into R2. And then I have my lower triangular. So my upper triangular, I'm going to start with negative 2. And so I'm going to use the bottom row. So R1 plus 2R3 into R1. So that's me 1, 3, negative 2 plus 2 is 0. 4 plus 10 is 14. 0, 1, negative 1, 0, 0, 0, 1, 5. And then I need to get that negative 1 to be a 0, and I can play off of the last row again. So I'm just going to add the 2. R2 plus R3 into R2. So 0, 1, it's going to be a 0. 0 plus 5 is 5. So now I have my second solution. Well, second part of my solution. I also have that x2 is 5. And so from here, I could just plug in and I get my answer, but I'm going to go down and get my reduced row echelon form. So I need that 3 to be a 0, so I'm going to play that off of the second row, since that's the column that I need. So R1 minus 3, R2, put that into R1. 1, that's going to be 0, 0, 14 minus 15. And so now I see that x1 is negative 1.